Here's the video summary for Chapter 6, Section 6.5 and 6.6. 6.5. Confidence intervals for a single mean. Note that this is primarily using the t-distribution. That's what we're going to go through today. If you know the true standard deviation, then you're going to use the central limit theorem and the normal distribution. If you don't know the true standard deviation, then you're going to use the t-distribution. Again, if you know sigma, then you're going to use this. If you don't know sigma, then you're going to use this. Let's look at an example. Again, the normal distribution calculator will do most of the heavy lifting for us. If we want to know the mean commute time in Atlanta, as in example 6.14, we gather data. Suppose we sample 500 different commuters, and we get a mean commute time of 29.11 minutes and a standard deviation of 20.7 minutes. Since our standard deviation was derived from our sample and it's not the true standard deviation, we're going to use the t-distribution. So, we go to the t-dist CI section of the Advanced Normal Distribution Calculator and enter in the information. Again, it's 29.11 minutes as our sample mean. Our standard deviation is 20.7 minutes, and our sample size is 500. And we want a 90% confidence interval. And that gives us about 27.57 and 30.65 as the limits of our confidence interval. Note this is a little bit off from what's given in the book. But from this we can say we are 90% sure that the mean commute time for all Atlanta commuters is between 27.58 and 30.64 minutes. And that's how you compute a confidence interval using the t-distribution. Section 6.6, test for a single mean. So in section 6.5, we're doing confidence intervals for a single mean. 6.6, we're doing a hypothesis test for a single mean. It works in a very similar way. If we know the true sigma, then we're going to use the normal distribution. If we don't know the true sigma, then we're going to use the t-distribution. Over here, that means if we know the true sigma, we're going to do this, p-value, sigma known, and if we don't know it, then we're going to do this with the t-distribution. I'm actually not going to do an example worked out in the book. I'm going to do exercise 6.141. How many social ties do you have? From other means, it was determined that there are U.S. adults on average have 634 social ties, and we wanted to know if cell phone users have a different number of social ties. 1,700 people were surveyed who own cell phones, and that mean, the sample mean, was 664 social ties with a sample standard deviation of 778 social ties. Now the question is, from the sample, we have a mean of 664, which is higher than 634, but is it enough that we can conclude or support the claim that in general, the average number is different from 634? These are the facts. Our hypotheses, stated explicitly, are the true average number of social ties of a cell phone user has is 634, or the true average number of social ties a cell phone user has is not 634. So this is a two-sided extreme. We could have also written it as such this way. Note I use the exclamation point equal sign to mean not equal to. Just easier to write. Now because it's a two-sided direction and extreme, we have a two-tailed test. Since our sample size is sufficiently large, we can use the t-distribution in the advanced statistics calculator. We could actually use it anyway in the normal distribution if we wanted to. And we just enter in the numbers here. Okay, the null hypothesis mean is 634. The sample standard deviation is 778. It's a very large standard deviation. Our sample mean, 664, and our sample size is 1700. This is a very large sample size, so we should get somewhat clear results, even though our standard deviation is large. And again, we have a two-sided extreme, because we just want to know if it's different, and we get about 11.2% or 0.112. Because our p-value is large, at say a 5% level of significance, we'd retain H0 and conclude that we don't have enough evidence to support this claim that the average number of social ties for a cell phone user is different from 634. I like this example because a few things. One, we have a very large sample size. Two, we have a very large standard deviation. Those two things often work in conflict with each other. But also, we have a null hypothesis that says the number should be 634, and the alternate says that it should be different from 634. And if we were just to look, it seems like 664 is far enough away from 634 that we should support the alternate. But when we actually get down to it, we see that we should actually be supporting the null. Our standard deviation is very large, which means there's a lot of variation in results, which would mean that maybe we have very large numbers. Some people might have 800 or 900. Others would have maybe 200 or 300. And that means that the variation in results is so wild, we can't actually conclude definitively that it's not 634. Alright, and that concludes the summary and examples for 6.5 and 6.6. We have one more video left just to go through some things related to the project, and I'll talk to you soon. Take care.